All right, so wait a little bit longer here. I think everybody's in. Okay, so hopefully you had some time over the weekend or earlier this morning or later in the day on Friday to kind of watch that 20-minute or listen to that 20-minute kind of introduction to chapter 4 material, which is going to be all about probabilities. Also, before we get going, just to double check once again, since we're not in my usual environment, everyone can hear me okay? I need to be a little bit louder, or I mean, no one's in the house with me right now, so I can shout as loud as I want. Does it sound okay? Okay. So I kind of just introduced the idea of like what the underlying thing is with probabilities. I related it pretty much to what we did with relative frequencies. It's very, very similar. In fact, Wednesday, I think we'll probably get to some Excel stuff where I'll show you how we start to build some probabilities off of a data set. And that really looks kind of similar to what we're doing with relative frequencies. And I think you'll be able to see kind of that connection maybe a little bit clearer. So I left off talking about some of this probability notation. So, or that's kind of the slide I left off on in that extra video that I posted. So we'll just go through a couple definition stuff with probabilities and how we can start to think about what this looks like. So if I've got, here I've got, maybe I'm interested in some event A. So we talked about there's this huge experimental outcome space. So if I'm thinking about this huge experimental outcome space, there's all these different possible outcomes that when I run this experiment, I could see. Right? So if I'm rolling a die, the possible outcomes I could see is 1, 2, 3, 4, 5, or 6. Right? That's my experimental outcome space. Maybe I'm only interested in a certain event. And that event is only saying certain numbers. So maybe my event A, so I should double check if that marker works. I guess we'll go with blue here. My event A, right? And I'm not going to switch back and forth on the video here. Hopefully it's big enough you can kind of see it down here in the corner. If you have any questions on what I'm writing, it's not big enough, let me know. In fact, let's see if I can grab this here, make it just a little bigger down here in the corner. So if my event A, and these squiggly lines is just saying kind of like this is what's in event A. So maybe in event A, it's that when I roll that die, when I perform this experiment, I see either a 2 or a 3. That's what I'm interested in, okay? So if that's event A complement really just means every outcome that I could see from performing this experiment that's not in whatever event A I've defined, okay? So I defined event A as saying either a 2 or 3, right? That's the two outcomes. A complement would be, what else could I see that's not a 2 or 3? Well, a 1, a 4, a 5, or a 6. And these squiggly lines aren't looking great. You might hear a dog in the background, I apologize. It's probably getting a package or something right now. So, hold on. These are the things that happen with Zoom. Hey! What? All right, sorry, part of the interruption. So, there's a complement. It's just every outcome not in A, okay? The next thing we have in terms of the notation that we're going to be using is A union B, okay? So I'm going to turn this here just a little bit. So let's say I also have event B here, and I define that as seeing either a 3 or a 4. Might kind of look like a 9 there. A 3 or a 4. All right? So if I'm interested in A union B, what that means is it's everything that's going to be in A, but also it could be in B. So in either one of them, right? So I'm going to erase the A complement, just give myself a little bit more room here. But if I was interested in A union B, right? When I write that union, right, it's really a set sign. It's not actually a U, but for all intents and purposes in this class, think of it as a U, right? It's a U, and it means this is the union of the two events. Or another way we can think about it is it's in either A or it's in event B. That's how we read that sign. Is it A union B? Or you can think about that, is it in A or is it in B? Right? So I want the union of these two events. Let me see if I can get this glare to go away a little bit better. There we go. If I look at these two events, what numbers is in either A or in B? Well, 2 is in A, 3 is in A, 3 is also in B, and 4 is in B. Well, those are all the outcomes that are in either one of them. So the union of those two events would be, I could see either a 2 or a 3 or a 4, and any of those values are in A or they're in B. They could be in both, that doesn't matter for the union, they just have to be in one of them. Right? Okay. It's a little bit different than when we go to the next thing, which is A intersection B. So A intersection B, right, is kind of this upside down U looking thing. Once again, it's a set symbol, but for all we can think about it as kind of an upside down U. Some people say, how do I remember, you know, the union? Oh, gosh, why is this glare so bad? Switch this around a little bit. There you go. So how can I think about the difference between the two? Well, the U sign is or, the upside down U is and. You can almost think about if I like put a little line across that, it would look like an A. So that upside down U kind of means, is it in A and is it in B? So if we look at events A and B up here, what's the only number that's in both of them? Or what's the only number that's in A and in B? The only number in both of them is 3. Okay? So that's kind of the difference between A union B and A intersection B. So here we've got the U, which represents it's in A or B, or another way to think about that is we can read that as A union B. And then down here, this is A intersection B, right? Or is it in A and B? Okay. So that's kind of or how we read this notation. That's kind of what it all means. The last thing we can think about, which is a little bit weird, and we'll focus on this more as we kind of move through probability material, but we have this A conditioned on B, right? So instead of thinking about kind of what this looks like in terms of set theory, I'll try to almost describe this to you. I'll describe this to you in terms of probabilities. And like I said, we'll go more in depth into this once we start talking about different the multiplication rule. But A given B, right, or A conditioned on B, and this straight vertical line is like a conditional line, right? So the way we read this is, what's the probability, like once I put a probability sign in front of here, what's the probability we see something in event A given, right? So you read that vertical line as given that B has already occurred. Or given whatever's after this line, you assume that has already happened. Assuming that that has already happened, then what's the likelihood, what's the probability that you now see A occur? And I'll tell you how this can kind of change things, right? So let's say I have no information, and I say, what's the probability if I roll a die that I see a 6, right? Excuse me, well, there's 6 possible outcomes. So when I roll that die, each one's equally as likely. I kind of mentioned this in the extra video, kind of it's the classical method, right? Everything's equally as likely, so I just assign 1 over n, or 1 over the number of outcomes. Well, 6 possible outcomes, so the probability that I roll, say, a 3, right, is 1/6. Okay. So no information, the probability if I roll a die comes up as a 3, 1/6. And now let's think about the events we had. If I tell you that, what's the probability, and if I'll even keep it as this. What's the probability? Let's say we keep A the same. It's do I see a 2 or a 3? So it wouldn't be 1/6 there. We would just add up the probability of both outcomes. So 1/6 plus 1/6. So there, the probability I see A occur if I roll a die. Probability I see a 2 or 3 would be 1/6 plus 1/6, or 2/6. Right? Now let's assume I give you some additional information. I tell you, okay, given that I'm not telling you which of the numbers in event B have occurred, but I'm telling you event B definitely has occurred. Given that event B has occurred, now what's the probability you see a number that's also an A, that is an A? Well, if I look at event B, the only possible outcomes I could see would be a 3 or 4. So in my head, I know, okay, I've been told that B has occurred. Given that B has occurred, so I know either a 3 or a 4 was rolled. Let's say someone's got this in their hand, right, and they're not showing to go. I can tell you event B has occurred. And it's okay, so what's the probability now that you know that event A has happened? Well, if I know either a 3 or a 4 has been rolled, right? Now the probability that event A occurs, that either a 2 or 3 has been rolled, well, I know it's either 3 or 4. The only way it can also be an A is if it is a 3. So given that B has occurred, now the probability that in event A would have to be out of 3, so it's a 50-50 chance, right? I know where a 3 or a 4 is rolled. I don't know which one, but if a 3 was rolled, I'd be an A. If it wasn't rolled, you know, I'm not. So there's a 50-50 chance there. So this conditional probability is really going to change some of the underlying probabilities that you would see, because it's basically like anytime you have more information, you're always going to be able to make a better prediction, right? So that's the general idea of conditional probabilities. We will talk, like I said, more about that kind of moving forward, but kind of introducing that here, that's where I'll leave the discussion for now. Any questions over any of that notation? Just anything that I can say that you want to see something I wrote or have questions over something I wrote down? Okay, all right. So another way that we'll be thinking about these things are using Venn diagrams, right? So when I look at Venn diagrams, what I want to think about is this rectangle represents the entire experimental outcome space. So if any of you watched that video I put out, hopefully you picked up on this, or I might even ended class on a Friday. If I have every single possible experimental outcome, right, and I add up the probabilities of all those outcomes, what should those add up to? If I look at every single possible experimental outcome, I add up all those probabilities, so someone says should be 1, right? It's very similar to the idea of the relative frequencies. When we looked at the probability, the relative frequency of every single possible kind of bin that we had, well, the probabilities have to add up to 1 because we've covered every single possible thing that could be counted. Same idea here. If we look at the entire experimental outcome space, that represents the probabilities of every single different possible outcome there. And so we know that that experimental outcome space is 1. So think about this rectangle as having an area of 1. That's almost like an easy way to think about it. Within that rectangle, which represents all the possible experimental outcomes, here, this circle just represents event A, and this circle represents event B. So if I'm thinking about event A, I could shade in that circle. Event B, I could shade in this circle. Now the intersection of the two, or A, what is in A and also in B, right? This is our intersection sign. It has to be both in circle B, but also in circle A. So that's really going to be visually where those two things overlap. So kind of notice here where those two circles overlap, which represent our events. That's the area we get shaded in. You can almost think about the numbers I was doing, right? This whole circle represents seeing either a 2 or a 3. This whole circle represented either seeing a 3 or 4. And where they overlap is that outcome of seeing a 3. Now the union of the two events would be any outcome that's in event A or in B. So it could be in A, but not in B, which is kind of like this half crescent moon here, right? These are all the outcomes that are in event A, but not in event B. Here, this other crescent moon, it's a crescent moon, it's like backwards and things, but everything that's in an event B, but not in A. And then where they overlap, everything that's in both of them, right? So kind of everything that's in either one of the circles, that represents A union B, or it's in A, or it's in B, right? So those things are all kind of interchangeable, union, or, and then on the flip side, kind of the intersection, or and, okay? So I'll be using kind of those Venn diagrams a little bit as we kind of think about different things. But the next thing I want to bring up is contingency tables. Right? So I'll minimize myself here a second so I can actually see everything in that table. I don't know, maybe you don't want to see me while I'm talking, but it gives somewhat of a personal feel, I feel like. The way we read these contingency tables are whenever I look at one of these top 4 left cells, okay? These top 4 left cells represent probabilities of intersections. So those top, I'll say this a lot, but those top 4 left cells represent the probability of intersections, okay? So this would be the probability that something is in event A and it's in event B. This would be the probability that something is in A complement and in B complement, right? Or instead of and, right, that kind of upside down U. Now the total columns represent the probability of just that event themselves. So if I look at this 0.6 here, that's the probability that just A occurs, or that, you know, I'm just thinking about what's the probability as you see A. No intersection, no union, no conditional, just what's the probability of A? Go over to that total column, okay? What's the probability of B complement? Go down to that total column, or I said, go down to that total value, right? So that's kind of how we read these, right? And what should be true is if I take the probability of A and the probability of A complement, well, if I go back here for a second, if I think about everything that's in this circle A, and then everything that's not in that circle A, well, that fills up the entire experimental outcome space. And I said the area of the entire experimental outcome space is 1 because it represents the probability of every single possible outcome. So if I took the probability of A and I added the probability of A complement, those should add up to 1. Right? So your contingency table, your totals, if you've done things correctly, should always add up to 1. Okay. Now, if I just think about event A, and I told you that the probability of it is right here in the total column, but how did I get that total? Let's say I left off this total column and this total row at the bottom. How could I get those values with just knowing these top 4 left cells? Okay. So this is, I'm trying to give you a visual of this, but you kind of notice I have here, if we would have added up those 2 intersections, or kind of add across the rows, notice 0.4 plus 0.2 is 0.6, 0.1 plus 0.3 is 0.4, 0.2 plus 0.3 is 0.5, so on and so forth, right? So where does that kind of come from? Well, I'll give you a full screen view on this one. So if we're thinking about why that's the case, use a green marker this time. I think this one shows up in the view. So let's say we've got this experimental outcome space. It's an area of 1. And I've got event A here. So this is event A. And I've got event B here. So if I think about this, where is B complement? Let me try to use a different color. I don't know how well this color is going to show up, but everything that's not in B is B complement, right? So if I look at circle B and I start to say, okay, what's B complement? Like I said, there's a little bit of color difference. Hopefully you can kind of tell, but all these straight lines, these blue lines, right? Those blue lines represent B complement. So let's think about this. If I look at event A, so I'm looking at this circle here, everything that's in A and in B, or A intersection B, is going to be where those 2 circles overlap, right? Okay, that's the intersection of A and B. But now what happens if I think about the intersection of the intersection of A with B complement? Well, everything that's in circle A, but also in B complement, would be everything in circle A where there's blue lines that go through it. So everything that's in A, but also in B complement, would actually be this guy right here. Well, notice if I add those 2 guys together, right, so this represents the intersection of A and B, or I'll try to keep the colors consistent here. So the green was the intersection of A and B. Blue was the intersection of A with everything that was not in B, or B complement. So if I add these 2 things together, they should just give me that entire circle A, or the probability of A and B plus the probability of A and B complement just add up to the probability of A. Okay, so you can kind of hopefully see the colors a little bit better. If I hold it here for a second, especially if you're going back and watching this, you'll be able to kind of get a good look at that. Okay. So that's where that comes from. So now if we take a look at that contingency table, we'll notice, give me 1 second here, got markers everywhere. So if we notice, if I look at the intersection, remember these top 4 left cells represent intersections. So we just said, if we look at the probability of A and the probability of A and B occurring, so that's right here, and add to that the probability of A and B complement, right? We add those two together, we should just get the entire circle A, or the probability of A right there of 0.6. So that's why if you add kind of across the row here, you should be able to get that total, right? And if I add across the row here, I could draw similar things that show it's really just the same idea, that, you know, because the complement literally means everything else not in B or everything else not in A, excuse me, when I look at the overlap of A with B and its complement, the intersection of A with those two things should always add up just to the probability of A. So if I left off these totals, you should be able to add down the columns and across the rows to reproduce those total columns, okay? Any questions on that, or you want to see kind of what I had drawn there again, or just questions on anything before we keep moving? Okay, are we good with that? All right, so if I'm thinking about event B here, once again, I can get the probability by just going to the total, or if I didn't see the total column here, I could add kind of down the columns, add 0.4 to 0.1, and I would get that 0.5. Right? It's a similar idea, right? The picture I just showed. What if I want A union B? Okay. So A union B, there's 2 ways we can think about it. Let me think how I want to do this. So I'll show you one way now, and then after we talk about a rule, I'll come back to this and show you a second way. Yeah, actually hold off on that. So the first way is not maybe the greatest kind of way to think about this, but it might click with some people, right? So if I'm looking at the union of 2 events, and actually I will kind of draw you something here real quick just to help. Okay, so let's say I have another space where I've got this huge experimental outcome space. Right? I've got event A, and then over here I've got event B. If I think about A union B, on that earlier slide we said that was everything in each one of these circles. I'm going to break it down into 3 components first to kind of give you a different look at this, right? So if it's anything in either one of these circles is A union B. But I can break A union B down into 3 components. So first of all, what is everything that's in A but not in B? Well, if it's in A, oh, but it can't be in B, it would actually just be this kind of crescent moon here. So what that represents is it's everything in A but not in B. So it's the intersection of A and B complement. I then say, okay, what's on over here? Well, this is everything in B, but not in A. So that's everything in B and not in A, right? Or A complement. When I say not in A, that's A complement, right? That's the definition of the complement. I then say, okay, what's left here in the middle? Well, that was where the 2 events overlapped, which we said that was just the intersection of where things were in both A and B. So we've got these 3 different components, right? A intersection B complement, B intersection A complement, and A intersection B. So if I add those 3 components up, I should now have everything that's in those circles, right? So let me get rid of this chat real quick. So I should have everything that's in either one of those circles, okay? So we go back here. I'll try to hold this up as a kind of a reminder. All right, so these are the three things that we're looking for. So the first one is A intersection B complement. So we go here, A and B complement. Well, that's 0.2. B and A complement. So B and A complement is 0.1. And then A and B is 0.4. So if we add up these three, we should get the union. So 0.2 plus 0.4 plus 0.1 should be 0.7, right? Or I kind of say, oops, I'll go back to that slide in a second because I thought I read that wrong. That's intersection. I was talking about the union the whole time. Someone should have spoke up and let me say, hey, you're reading that wrong. So here's A union B, right? And that's kind of what I just showed you, right? It's each one of these three components. We can break it down, right? Now, another way that you can think about that, and it's like not technical, I guess, but it's a way that'll work on these contingency tables, is if you go to, if you're looking for the union, if you go to the intersection of those two events and like make an L and add those up, it'll give you the union. So if I would have went, I want the union of A and B, so I go to the intersection of A and B, make like a L, right, and add those up, that's my union. That's like a, not a technical way to remember it, but it will work. No, but I was just thinking about the intersection of A and B. I've kind of already covered this. This is why I forgot to put this slide in because I usually always go over it too soon. But right, A intersection B is just A, intersection B would be that 0.4. I want the intersection of the complements, right? That would be kind of down here. Because those top four left cells all represent intersections of whatever their row and their column headings are. Okay? And then we broke down the union into those three different components. And I don't know if we'll get there today or Wednesday, but I'll show you a different way of thinking about the union as well. Okay? So this might be a sample question I might put on like today's online quiz, which is I need you guys to start thinking about and know how to read these contingency tables, right? So just checking the chat there. So if I asked you instead of A and B, I have what? R1 and C1, and I call the complements C2 and R2. Doesn't really matter how we label them. What's the intersection of R1 and C1? Well, R1 and C1, that intersection is 0.4, right? Once again, these top four left cells all represent intersections, or this upside down U, or and, in R1 and C1, okay? So that could be a sample question you see, just starting to think about how do I grab these intersections from this contingency table, okay? Okay, so we will get to it today. I forgot what order I had. So if I think about the union of A and B, it's the same as saying the union of B and A, right? If something is in A or B, it's the same thing as saying is it in B or is it in A? Doesn't matter which order I say that in. So if I flip these, it's still talking about this same white shaded area here, okay? That one's pretty easy. That one I don't think should give anyone too much trouble. Same thing with the intersection. Order doesn't matter. If something is an A, and like if I'm over 30 and I don't know, have brown hair, I also have brown hair and I'm over 30, right? Like it doesn't matter which way I say that, like it's the same thing. We got animals all over the place. I don't know if you guys can hear that. So it doesn't matter which order I say it in for the intersection or the union. Now I always thought this was like a fun little meme to kind of just break things up, right? Talk about the intersection of when someone says it's fine and when it's actually fine, right? Slim overlap there. Okay, so I kind of already mentioned this one, but here's a way better visual of what I was saying, which is that if I think about A and I think about everything not in A, those have to fill up the entire experimental outcome space. So if I think about the entire experimental outcome space, here's A. The blue area is everything not in A, or A complement. So I think about the probability of A and the probability of A complement. Well, when I add those two together, I have to get 1, right? It fills up the entire experimental outcome space. So all I'm really doing there to get that complement rule, right? So what I just said was, if I take the probability of A and I add to that the probability of A complement, well, we just said those fill up the entire experimental outcome space. So all I did was rearrange this equation a little bit. I'm going to subtract the probability of A from both sides. And then what I'm left with is that the probability of A complement will always be just 1 minus that probability of A, right? So anytime I know the probability of A, I automatically know the probability of its complement by just subtracting the probability of that event from 1. Sounds pretty easy. That's not too tough of a rule. I think this here, you get like a really nice visual. When I don't have event B up there anymore, you can see that I took what's in event A and what's in A complement, I added them together, they add up to 1. And if I arrange that equation a little bit, the probability of that complement is always 1 minus the probability of the event. Okay? And this will kind of sneak its way into a lot of what we talk about, even in kind of future chapters. All right, so this is what I wanted to make sure we get to an end on. We can get the cat to stop meowing. I got too many animals here right now. So if I think about A union B, okay, this was, I already showed you what it looked like on the contingency table, but I'm gonna give it another look at it, right? So this is a way in which we can calculate what the union is, right, without it being explicitly told what it is. So if I think about this, if I look at the union of A and B, it's everything that's in either one of these circles, right? So I shade in this white area. But if I remember, this area in the middle is A intersection B. So a lot of people think, well, to get the union, wouldn't I just add up the probability of A and the probability of B? So why am I subtracting the intersection of the two? Well, if I think about this, if I took the probability of A, so I took this circle, and then I added it to the probability of B, I've actually double counted what's in both of them. So if I've double counted it, how can I make sure I only count it once? Subtract it out one time, right? And so because if I just add the probability of those two events, I'll be double counting anything in the intersection. The way in which I can get that union is add the probabilities of the events together and then subtract out what I double counted, which is that intersection. Or A intersection B, A and B, what's both in A and B, okay? Now, if this is true, right, there's another way to kind of think about this. I could take what's in A and then subtract out the intersection. So I'm only getting this crescent moon. So I could take the probability of A, subtract the intersection. I could then take the probability of B, but don't count the intersection. So I only want this crescent moon. So take the probability of B and subtract out the intersection. Well, and then to count the intersection only once, well, now I have to add that back in. So I add the intersection, these cancel, and I'm still left with the same equation. It's just a different way of thinking about it. I don't like this way of thinking about it as much, but some people it clicks with, so I always just kind of mention it. To me, it makes a little bit more sense to think about, yeah, if I just added the probability of the two events and I double counted something, I double counted what was in both of them, just subtract it out once. That's the way that kind of clicks with me. But some people think about, oh yeah, how would I get this, only this crescent moon, only this crescent moon, and then what's in both? Well, this crescent moon is the probability of A minus the intersection. This crescent moon is the probability of B minus the intersection, and then I'd add in that middle part again. Right? So just a different way of thinking about something. It doesn't really matter. You arrive at kind of this same equation. Okay. So this is where, if we go back to a contingency table, let me see where I have in these slides here. I started kind of jumped to mutually exclusive. I don't think I. Yeah, I want to go back all the way up here, okay? So if we go back to that slide where we had A union B, and I showed you, well, you can find it this way. Well, there's another way to find it, right? We just had this equation, which is if I want the union, I can take the probability of A plus the probability of B minus the intersection, right? So let's try to kind of remember that, and we'll go back to that other contingency table. In fact, it's going to make this easier. I'm going to cheat and drag this down for right now. so we can see and kind of go back and forth. Right? So we have the union. I just said this equation should find us the union. Well, the probability of A plus the probability of B would be 0.6 plus 0.5, so we're at 1.1. We know that can't be right because it's more than 1, right? The highest probability we should ever see is 1. So we have one more thing to do, which is subtract out the intersection. So we added the probability of A to the probability of B, 0.6 plus 0.5. And then we subtracted out the intersection, which was what's in both, which is A intersection B, which is here, which is 0.4. So 1.1 minus 0.4, right, gives us that 0.7. Right? If you're kind of, hopefully if you're taking notes, you're following along, you're writing that down, right? We're really just filling in the values of this equation. We found the probability of A was 0.6, so you could write that in. We found the probability of, why don't you subtract the intersection times 2? I'll come back to this in 1 second. You find the probability of B, which is 0.5. You would write that in. You find the probability of the intersection is 0.4. You would write that in. So 0.6 plus 0.5 minus 0.4 should get 0.7. But if we think about the old way in which we said to do it, like break it down into 3 components, or the non-technical way of finding the intersection and making an L, well, what did those add up to? 0.2 plus 0.4 plus 0.7. So it'll give you the same answer every single time. It's just a different way of thinking about it. I personally think once you get to remembering and kind of understanding this equation, this is an easier one to grab from the contingency table, because it's very easy to find the probability of just an event itself, and then you're only looking for the probability of one intersection. Okay. So the question was, why don't you subtract out the intersection twice? Okay, you got it? Yeah. So the reason why you don't subtract it out twice is because you still have to count it once, right? So even if I double count something, I still want to count it 1 time. So it only subtracted out once. Yep. Any more questions on kind of that before we keep moving forward here a little bit? Are we on time? Oh, okay, we're good. Okay. All right, good deal. Okay, so I think I've mentioned this actually already, and we were talking about building the bin lengths. I mentioned the terminology of being mutually exclusive, right? So something is mutually exclusive if it can't be in both events at the same time. So if I can't be in event A and event B, then the intersection is 0, right? What it really means is, there we go, there's my picture. What it really means is that if I look at this experimental outcome space, everything that's in A could never be in B, and everything that's in B can never be in A. There's no overlap between these 2 events. So I think about my rolling the dice. If I had defined event A as seeing a 1 or a 2, and event B as seeing a 5 or a 6, what's the probability I see something, the die rolled and that something is in A and B? Well, there's no number that fits that criteria. So the lowest probability we can see is 0. So if things are mutually exclusive, it means they can't happen at the same time. So there's no overlap in those events, which means that the probability of seeing something be in both of them, or A and B, or A intersection B, the probability is just 0. And that makes our life easier, right? Because now if I'm thinking about if I want the union of A and B, well, there's no overlap, right? I wouldn't be double counting anything. And I can leave this in here, but when I go to subtract the intersection, I'm always going to be going to subtract 0. Whoops, I spoiled my meme. I'm always going to be subtracting 0, so it doesn't matter. I can kind of ignore it, right? It almost makes things easier. Now, if I look at a contingency table, what's the only way that I know 2 events would be mutually exclusive? I'd have to see a 0, right? Because if I don't see a 0 here, then there's some overlap. Remember, these top 4 left cells represent intersections. So if A intersection B is anything other than 0, there is some overlap, which means they're not mutually exclusive. Even if it's 0.0001, there's some overlap, which means they wouldn't be mutually exclusive. But if the intersection of those 2 events, there's no overlap, and the probability is 0, we know we have mutually exclusive events. Okay? And so then the example I give to kind of date me a little bit is in the 90s, phone internet access were mutually exclusive events, right? So you had to use your phone line to get in the internet. This got me in a lot of trouble in middle of high school when I'm trying to use the internet all the time and someone calls and they just get a busy signal, right? So you can't have these 2 things happening at the same time, unless you then wanted to buy a second line, and then your parents are telling you we don't need this, and it was a whole thing. So this is the idea of mutually exclusive, and you can kind of see it relates a little bit to this equation, that it makes it a little bit easier. Okay? So that shouldn't be too bad. So the next law I'm going to talk about is something that we'll deal with a little bit, and it's really just kind of pushing forward. It's not so much a law as we could just think about the experimental outcome space a little bit more. So let's say I've got everything that's in A and everything that's in B. So this white area here represents A union B, right? It's in A, or it's in B, or it's in both. We don't care, it's in one of them, right? Everything that's not in that union is actually the probability of the complement of those two events. So I'll try to give you a visual here as to why that is the way it is. So let's say, and I'll try to use the two colors here once again, and hopefully it'll be a little bit clearer. So let's say I've got this experimental outcome space. Here's A, right? Here's everything not in A. In fact, I'll leave them as stripes for right now. If I need to shade this in, I will, but I don't think I need to. Hopefully it'll get the point across. Here's B. Here's everything not in B. Okay? So it might be a little hard to see, but if you kind of try to look at the areas where those blue and green lines would overlap, well, notice there are blue lines here. No, wait, hold on. There are blue lines here, but there's not green lines here because the green lines represent a B complement. So these lines represent A and B complement. So the only place where we have those lines happening, both happening, is everything kind of outside of that union. Well, when I said, where do those green and blue lines kind of intersect? Here, I'll do this up as I'm talking. When I say everything where those blue and green lines intersect, well, those blue and green lines simply represented A complement and B complement. So where they overlap would be intersection, right? So the intersection of A complement and B complement is just the entire area that would be outside of those two events, right? So when we go back to the slide here, what we're saying is, look, if I take the intersection of those two complements, it's everything outside that union, and I add that to the union of those two events, I've filled up the entire experimental outcome space. So the union of those two events, which is this white area, shaded white area, and the intersection of their complements, but I just kind of gave you some more intuition as behind why that's this blue area. And if you're not completely sold or clear exactly why that is, just accept for a fact that that is what it is, right? If you just know that I tell you that's what it is, you can clearly see that that blue area and the white area add up to the entire experimental outcome space. So I take the white and the blue area, add them together, I should get 1. Well, I can break the union down a little bit more, right? If someone doesn't tell me exactly what the union is, I know I can find it by adding the probability of A to the probability of B and subtracting out what I double counted, which was the intersection. So if I just substitute in for that union, that equation we were using earlier, I now also know that the probability of A plus the probability of B minus the intersection, plus this blue area, the intersection of the complements, those also would have to then add up to 1. Because I'm really just replacing this formula here. It's kind of like you're substituting in formula for what that union is. Okay? So we could then push things a little bit further. Even if we weren't given the union, we could then maybe find out, if we had 3 of these missing components, we could always find the 4th, right? So maybe I tell you the probability of A, the probability of B, and the intersection of those two, but I don't tell you the intersection of the complements. Well, if I have 3 values here, and I know they add up to 1, it's just a little bit of algebra moving things around to solve for what this probability of the intersection of the complements would be. Right? So at this point, you would have to be comfortable using a little bit of algebra, but once you are, hopefully that's not too bad. Right? So let me see. So here would be a good problem where we could kind of test that. And we'll go back to the multiplication rule when we start class on Wednesday. So if I wanted the probability of B here, right, how could I find that? Well, I just had this equation, which I was told was, if I take, so if we go back here, if I take the probability of A plus the probability of B minus the intersection, oh, I got to write smaller here for you, sorry. If I take probability of A plus the probability of B minus the intersection, add to that the intersection of the complements, right? Then all those should add up to, should equal 1. So from there, I just start plugging things in. Right? I go back down to my problem. I know the intersection of the complements is 0.3. I know the intersection of the complements is 0.3. The intersection of the two events is 0.1. The probability of A is 0.5 up here. I'm just plugging things in. And now the probability of B is the only thing I don't know. So if I rearrange, let's just rewrite this equation. 1 would be equal to 0.5 plus the probability of B minus 0.1 plus 0.3. Now it's just algebra. So 0.5 plus 0.3 is 0.8 minus 0.1 is 0.7. So I subtract 0.7 for both sides. And now I've got 0.3 is equal to the probability of B. Right? So I've just done algebra there. That's all I've done. Just rearranging things. And I end up being able to solve for the probability of B. So if you kind of want, you have this on this slide as well, kind of just as we plug these values in, it's maybe not quite as clear because I kind of maybe did some of the rearranging. So you have kind of the work I just did there. Kind of see as you plug this in and rearrange the equations a little bit, you can pretty easily solve for what that probability of B is. Now, another way to do that is before you plug the number in, is to like rearrange this equation so you're solving for what your unknown is. I personally think it's easier to plug the numbers in and then rearrange things to solve for what you want to find. Okay. Let me see. Okay. So here's another one. I won't walk through this one, with you since classes should be about over here. But it'd be some good practice to kind of, you're just solving for a different component. You would really do it the same way. You've got the answer to kind of double check yourself if you want to check your work. This is really just another sample question that would be good to work through before you do the online quiz, because I'll probably give you something that looks like this on the online quiz. We have one, we have one that we already did here. We're solving for the probability of B. Only difference here is I tell you the probability of B in this one, and you're solving for the intersection. So that's really the only difference, just another practice problem as you're going into the online quiz. If you have any questions over any of that, let me know right now. We can kind of end with that. So, are there any questions on that or anything kind of coming up? I will say that exam date, which is supposed to be next Friday, I'll have a better answer by the end of the week. I'm thinking about whether or not I want to move that, maybe just limit some of the material that you would usually be on it, or kind of push it to that following Monday. I haven't, I'm finally kind of last couple of days I've had my mind right, so I'm still thinking about exactly what I want to do there, but I'm just making you aware that might get moved forward one day, right? So it won't be any earlier, but it might be kind of that next class later on Monday. Okay. Any questions from me? So you guys should be hopefully getting closer to completing those Excel assignments. And then you have that Connect assignment, which I pushed kind of the due date up to, I believe it was, what's today's date? Did I push that up to Friday? I pushed it up a day. No, you guys you have plenty of time to do that Connect assignment. We've covered all the material for us. All this probability stuff shouldn't be anything on those previous 2 homework assignments. So there's no more questions for me. I'll kind of end the recording and then I'll leave Zoom up if you have some questions that you want to ask afterwards.